We'll move on to the next session. I request Dr. K. Subramaniam sir to introduce our resource person, Dr. Maximi, from the Institute of Applied Physics, Friedrich Schiller University, Jena, Germany, to give the invited talk. Dr. K. Subramaniam sir.
Yes, ma'am. Am I audible to you, ma'am?
Yes, sir. Yes, sir.
Good afternoon to all here. It's a pleasure to invite Dr. Maximi Chambono, postdoctoral researcher, Institute of Applied Physics, Friedrich Schiller University, Jena, Germany, to deliver a talk on in-volume laser silicon interaction limitations, solution application. I take this opportunity to introduce Dr. Maximi Chambono. He has received his PhD degree at Aix-Marseille University, France in the year of 2014. His research area includes laser matter interaction, silicon photonics, optics. He worked as postdoctoral researcher at LP3 laboratory in Marseille University, France from 2015 to 2016. Currently, he is a postdoctoral researcher at the Institute of Applied Physics in Friedrich Schiller University, Jena, Germany, since 2018. He has published 50 papers in peer-reviewed journals. Once again, I invite Dr. Maximi Chambono to this session. We welcome you, sir. Now you take your space, sir.
Thank you very much for your kind introduction. Can you hear me?
Yeah, I can hear you, sir.
Yes.
Amazing. Then I'll try to share. All right. Can you see my screen now?
Yeah, I can hear you.
Yes.
Amazing. Thank you for your kind introduction. And first of all, I'd like to thank all the committee of ICHSM 2021 for giving me the opportunity to give this invited talk. So today I'm going to talk about in-volume laser silicon interaction, especially the limitations and what has been found so far to unlock some applications. So here is the outline of my talk. In the first part, I will briefly introduce the context about ultrafast laser silicon interaction. Then I will show how it is possible to hack microelectronic devices with underdense femtosecond laser produced plasmas. Then I will move to some permanent modifications, especially the functionalization of silicon with nanosecond pulses, and also with picosecond pulses afterwards for writing low loss waveguides. And finally, I will focus on some latest results we obtained on semiconductor-metal ultrafast laser welding. So first, let us introduce the context. So, as you may know, 3D ultrafast laser inscription in dielectrics is a proven technique. And essentially, the reason for this is that at the time scale of 100 femtosecond, or approximately, namely it's ultra short laser pulses, then you have an ultra fast energy deposition, which means an important thing, which is that you can distinguish and separate the causes, which are essentially the absorption of the photons, from the consequences, which are the material response. And in this case, it is, well, it's possible to achieve an extremely high degree of control on the modifications you can produce in dielectric materials. With, of course, applications which are numerous in fiber optics, microfluidics, micromechanics, data storage, more recently quantum computing, additive manufacturing, and surgery. So now, why should we intend to do this in silicon now? Well, here are a few answers. First, in terms of fundamental comprehension, it's always nice to improve the understanding of the response of narrow bandgap materials such as silicon under extreme conditions in terms of energy delivery, pressure, and temperature. Also, it's possible to determine some parameters that are difficult to access, such as the ionization dynamics, the plasma recombination, and the electron diffusion. So this is one answer. The second answer is that it would be quite nice for the industry to take benefit of the electrical properties of silicon. To date, there are lithography methods such as silicon on insulator, so SOI, but they are limited to 2D. And if you want to build 3D architectures, you need to do it layer by layer. You need also a clean environment, you need time, and it's quite costly. And on the other side, if one can develop ultrafast laser inscription inside silicon, it would provide a 3D flexible, fast, and contactless way to functionalize the material. And at last, for economical reasons, it would be good to extend 3D ultrafast laser inscription to silicon because of the constantly growing markets of here I give some examples: silicon photonics, quantum technologies, ultrafast microelectronics, sensors, photovoltaics, and so on. So is it the main question now is it that easy to transfer ultrafast laser writing to the bulk of silicon? Well, sadly, the answer is no. And if one wants to aim at ultrafast laser writing inside silicon, one will face different problems. First, they will face technological difficulties because first the silicon is not transparent to visible light, as you can see here. So you need for infrared laser sources. Also associated to this, you need some optics and detectors that are both costly and less efficient in the IR than in the visible. Here I give an example. For instance, your smartphone has roughly a pixel size of 1 micron, while a very good IR camera in gas-based is around 10 micron pixel pitch. But if this was the only reasons, then it would be possible to functionalize silicon with a laser. No, the main problem originates from physical limitations, especially when you look at the nonlinear refractive index of silicon. It is about 100 times higher than the one of fused silica, which means that during the propagation of the laser pulse, there will be a competition between carry effect on the one hand, which focuses the beam, and plasma defocusing on the other hand. So you focus the beam, the material starts to be ionized, and this ionization provokes a defocusing, which is called plasma defocusing. In other words, we are in the filamentation regime, which is a highly nonlinear propagation regime. I would not say the word chaotic, but you get the idea, I hope. And there are two consequences to this. First, as illustrated here, there will be a nonlinear defocalization. Here you can see that the focus is unambiguously shifted upstream towards the laser. Second consequence is a saturation of the intensity inside the bulk of the material, which is illustrated here, which means that when you take those two consequences together, there will be a delocalization of the energy deposition in the prefocal region. And as a consequence of this, one can conclude that increasing the laser energy will be a bad strategy for hoping to modify silicon and with ultra-short laser pulses. So, first, let me introduce how we can use the underdense plasmas that are produced with femtosecond laser pulses for hacking microelectronic devices physically. But first of all, I have to recall some basic operations of microelectronic devices. Here I take the the example of a MOS flash memory, which is defined by two logical states, essentially, the erased and the programmed states, so 0 and 1, which depends on the number of electrons present in the floating gate represented here. For basically erasing the flash memory, one can use negative voltage here and 0 elsewhere, and the electrons will be repelled towards the bulk, so the silicon substrate. Then afterwards, one can read the drain current as a function of the gate voltage, which is nothing else than a characteristic curve for stating 0 or 1 for the logical state of the device. And then if one wants to program the flash memory, you put basically 0 volts in the source and the drain, and in the source and the bulk, then a positive voltage to the drain and the control gate. And what will happen is that some electrons will migrate from the source to the drains, and some of them will be crossing the tunnel outside. And then when you read the device, you have this characteristic IDVG curve. One can also define the threshold voltage, which is the voltage for which the drain current is 1 microampere, and it quantifies the charge of the floating gate. So now the main question is that possible to emulate this process with laser radiation? To answer this, we have developed an experimental setup. I will not go too much to the details, but it relies on laser pulses, ultra-short laser pulses, so 100 femtosecond at 1.3 micron wavelength. Then we control the energy by means of a half-wave plate and a polarizer, focus the beam to the microelectronic wafer. And besides, we have two diagnostics. First, a stereo microscope in order to make some 4-point probe measurements and eventually program and erase the device in situ. And also here in green, represented in green, sorry, a microscope working in reflection for observing the microelectronic device and induce the plasma near the flash memory. So then when you perform some laser irradiation of the flash memory, here are the results. So you start here in solid blue and red lines, either erased and programmed. And you can see that there is clearly an effect of the laser radiation after 10,000 shots and 1 million shots, which means that there is a migration of particles, either electrons or holes, from or towards the floating gate. Then when you repeat this for different number of shots, here I represent the threshold voltage as a function of the number of shots, and you can see that the laser-induced programming and erasing phenomena are saturated somehow around, here it's around 5 volts. Interestingly, the curve describing the laser-induced programming and erasing follows the following function. So a sigmoid function as a function of the number of shots. That can be written like this, where A, B, and C are 3 free parameters. A and B are related to the boundary conditions, and C is the speed of the sigmoid curve. So the whole game here will be to determine what are A, B, and C. But first, how can we explain physically this kind of laser-induced programming? So let us consider the device and the associated band diagram. So the first mechanism occurring is the laser propagation, of course, which leads to the formation of a plasma in the silicon part by 2-photon ionization. Here is represented the 2-photon absorption. Then some electrons will be able to tunnel through the oxide layer toward the floating gate. Then this increase in the negative charge will lead to a change in the band diagram. And finally, the electrons and hole pairs that have been produced in the silicon substrate will recombine, and in the end you have more electrons in the floating gate than initially. And by repeating this from one pulse to another, you can clearly see that no electron migration will be possible once the band diagram will be completely flat. So in order to test this theoretical scenario, we have carried out two experiments. So the first experiment consists in using a control gate voltage, which is called polarization or bias. And here you can see the threshold voltage as a function of the number of shots for initially erased and programmed flash memories. And one can see that by having different bias, you can play on the final state of your laser-induced programming, which means that adjusting the polarization enables us to control the asymptotic VT value. This is consistent with the proposed scenario because the polarization will modify the initial band diagram. And we'll also observe the linearity between the threshold voltage and the applied bias. This allows us to determine A and B in the sigmoid curves, so the two of the three free parameters, which are related to the boundary conditions. So now we just need to evaluate what is C and how it can be related to the laser parameters. In order to do so, we have evaluated the influence of the laser energy, as you can see here. So same kind of graph, the threshold voltage as a function of the number of shots. And one can see that for low energies, the parameter C increases with the input pulse energy, so the laser energy, which is consistent with the two-photon ionization mechanisms, because the more the energy, the more the ionization, of course. One can also note that at high energies, there are some chaotic behaviors after a few shots, which are related to the degradation of the drain bulk and source bulk junctions. So here is the take-home message for this part. It is possible to hack physically microelectronic devices with infrared laser pulses. The polarization allows to control the asymptotic threshold voltage, and the laser programming speed depends on the pulse energy. So now a second study was oriented on the functionalization of silicon with nanosecond pulses. Why? Let us, summarize and evaluate the pros and cons of each regime. In the femtosecond regime, as we have seen, a low pulse energy is needed, and it is suitable for handling free carriers in a non-destructive way in microelectronic devices. However, the cons are, of course, it's impossible to modify the material inside the bulk. This is due to strong nonlinear propagation effects. But then if you go to the nanosecond regime, so 1 billionth of second, then it has been shown that it is possible to modify permanently the bulk of silicon. And this is due to the fact that when you increase the pulse duration, you decrease the intensity, and thus you decrease the nonlinearities inside the material. However, of course, more energy will be needed, and the main drawback is that you cannot separate, as I said in the introduction, you cannot separate the causes and the consequences, and thermal effects will occur during the pulse, which will lead to a high heat affected zone. So in order to investigate the influence of nanosecond pulse irradiation inside silicon, we have developed another setup relying on 1.55 micron wavelength pulses at 5 nanosecond duration. Then, same as previously, we adjust the pulse energy with a half wave plate and a polarizer, and we use the same microscope for positioning the geometrical focus with respect to the sample. And besides, we have another diagnostic, which is represented here, which is nothing else than Mach-Zehnder interferometer, which allows us to, well, it is at least transposed to the infrared at 1.3 micron wavelength, and it allows us to have phase images. So what is the phase shift of the laser-induced modifications, which are, well, essentially related to the refractive index change. Then here are some typical results we obtain when one tries to inscribe some lines inside the material at different scanning speed, so different feed speeds. What one can see is that for high and low speeds, you can see some black dots in the phase images, which are related to some negative phase shift, meaning that there are some negative index change, which have to be related to voids or microcavities inside the material. In stark contrast, when the writing speed is intermediate at 0.1 millimeter per second, one can see that there is no black dot in the line, and we have inscribed the structures. We can inscribe lines with a positive phase shift, meaning that there is a positive refractive index. The possible mechanisms for this are that the melted material induced by one pulse will fill the voids left by the preceding ones, meaning that in the end, when the material resolidifies, there are strong strain fields inside the material which provoke a refractive index change. And if one wants to evaluate the refractive index change, it's given by this expression here, and we find that it's on the order of 5 times 10 to the minus 3, which is theoretically sufficient for guiding light. So now the main question is, can we really guide light inside silicon? That would be a wonderful achievement, and this is what we endeavored. So here you can see a shadow graphic image of the written line. We have injected some infrared light inside the structure and detected the scattered light. And besides, we have carried out here in C and D some evaluation of the linear propagation in silicon, if one assumes that there is no guidance. So first, we can evaluate the numerical aperture of the potential waveguide, which is around 0.2. And the injection of the light with a high numerical aperture objective will allow us to have a strong divergence. So it's easier for us when we use a numerical aperture which is much higher than the one of the potential waveguide. It is much higher. It is much more convenient to see if light has been guided. And from the scattered light picture here, you can see that one can clearly see that some light has been guided, especially when you compare to the linear propagation calculations. So here are this is indeed the comparison between B and C. And you can see that in the experiments, there is more light than normally if you consider only free propagation inside silicon, meaning that part of the light has been guided. Especially, this is a semi-log scale, which means that the experiments are 100 times higher than the free propagation calculation. So in the end, light has been indeed guided with high losses. I will come back to this afterwards, but still, it's a first step. Then, Then with this positive refractive index change, it is possible to find some applications in the field of refractive index engineering for writing millimeter-long waveguides. As you can see here on the left, multiplexers for splitting and coupling the light, also called Y-couplers. We have inscribed diffraction gratings, and also we have performed surface texturings, either with negative index change or the positive index change corresponding to the waveguides, where we see some micro pyramid on the surface of silicon after selective chemical exchange. So here is the take-home message for this part. So with nanosecond pulses, we have decreased nonlinearities, meaning that it is suitable for modifying silicon in the bulk. It was possible to inscribe continuous lines of positive refractive index change. The refractive index engineering endeavors allowed us to demonstrate that it is possible to write long waveguides, multiplexers, and diffraction gratings. However, the losses were relatively high. And this is one point we addressed afterwards by endeavoring some picosecond laser irradiation for waveguide writing inside silicon. So here, the idea is to drastically decrease the losses, the damping losses of the waveguide, and well, access to some new applications. Here, the motivations are, well, are formulated in terms of questions. Like first, is it possible to write low loss waveguides inside the silicon with picosecond pulses? Because it's the intermediate regime between nanosecond and femtosecond. So it would be nice to investigate that. Then if it is the case, what is the refractive index change? And moreover, what's the origin of the waveguiding? So to answer this, experimentally, we have another setup relying on 1.55 micron wavelength at around 0.8 picosecond duration. Then classically, the beam is focused in the bulk of silicon. We have also one transverse microscope here represented, relying on white light emission and detected with an objective lens, a tube lens, and a camera, an InGaAs camera. Besides, we have another microscope here in green for positioning the focus with respect to the entrance surface, as you can see here. And with the first infrared microscope in a transverse way, one can, I hope it will start, yeah. So the idea is to write the waveguides from the back surface and move the focus towards the laser. So to take advantage of the brittleness of the exit surface. The typical processing parameters are a feed speed of 20 micron per second and pulse energy around 100 nanojoules. Concerning the waveguide characterization afterwards, so this is done post-mortem. We have employed another setup which relies on the emission of a continuous wave laser diode at 1.55 micron wavelength. Then the beam is focused to the waveguide and detected with a similar infrared microscope working in transmission as previously. And also we have another microscope allowing us to distinguish the scattered light. So here is typically what you see with the scattered light. So the damping losses can be estimated with this. And with the InGaAs microscope working in transmission, you can see the mode field and near field images. So what we concluded on those measurements is that we had some coupling efficiency of around 53%, a transmitted power of around 25%, which is consistent with the value we obtained from the scattering images. And moreover, the damping losses are around between 4 and 5 dB per millimeter, which is much lower than what we had before with the nanosecond pulses. Again, it was possible to demonstrate some functionalization of the material with a Y splitter, so a multiplexer, which is actually an additional proof of the light guiding. Here you can see the beam before it enters the waveguide, and here is the near field image, which corresponds to the measurements, and you can clearly see two different spots corresponding to the two different parts of the Y coupler. So the splitting ratio was 50-50, and here again the damping losses were 4 to 5 dB per millimeter. Concerning the refractive index change, we have estimated it by coupling theory with Helmholtz equation and overlap integral, and also, as you can see here on this video, some shift measurements that are detailed in a recent paper from our group. So the reference 2 here on these slides, which allow us to conclude that the waveguides are W-shaped, meaning that you start with a negative refractive index, then a peak of positive refractive index. And the maximum refractive index in this case is around 2 times 10 to the minus 3. And this is in good agreement with highly confined modes. So in the end, we have a single mode waveguide with low losses. Also, one could wonder what are the physical mechanisms related to the waveguide inscription in this case. And to answer this, we have carried out some material characterization at the nanometer scale with transmission electron microscopy and for different input pulse energy. What we saw is that clearly in the path of the waveguide, there are some local defects, which could be dislocations. However, the density of those dislocations does not depend much on the laser energy. And by performing electron diffraction, so selective area electron diffraction, we have noticed that there is actually no change, surprisingly, in the crystal structure of the material, which means that those waveguides may rely on strain induced by the presence of dislocations in the monocrystalline silicon. And here is the take-home message. First, we have demonstrated the exit surface seeded inscription of waveguides with picosecond pulses. The waveguides are low losses and the refractive index change is higher than 10 to the minus 3. And the nanometer scale analysis allowed us to claim that some strain was induced by the dislocations provoked by the laser pulses in the monocrystalline material. And finally, I would like to talk about our latest results, which basically are related to the comprehension of the filamentation inside silicon with picosecond pulses for semiconductor-metal ultrafast laser welding applications. So this is a kind of a hot topic in the laser processing community. to focus first on the context, ultrafast laser welding is, I mean, the context about ultrafast laser welding. Well, so first, joining materials is something essential for manufacturing, additive manufacturing for different industrial applications. And to do so, some traditional methods may be used, such as adhesive bonding, brazing, anodic bonding, and so on. However, those methods usually require, usually they show some important drawbacks. For instance, they may require another material or pressure assistance, or maybe they will face some aging or degassing problems, or they might just be not, the joint materials will be not too resistant enough to high temperatures. As a quite nice alternative, the laser welding technique has been developed, which consists of an energy deposition at the interface, as illustrated here, and it provides a fast, clean, and contactless way to join materials with a high strength between those. It was shown to be applicable in different material configurations, such as glass-glass, glass semiconductor, glass metal, polymer, and more recently, ceramic, as demonstrated in this science paper in 2019. However, in the semiconductor-metal configuration, there is nothing too convincing so far. So let us have a try together. Well, to do so, we'll employ the following setup, which again relies on 1.55 micron wavelength and around 10 picosecond duration laser pulses. Then we adjust the energy classically with a half-wave plate and a polarizer before the beam is focused at the interface between silicon and copper by means of an objective lens. And this objective lens is also part of a reflection microscope, which enables us again to position the geometrical focus with respect to the silicon entrance surface. Then after the laser processing, we evaluate the bonding quality in a post-mortem way by separating the two samples with an indenter. And when we try with a relatively intermediate, let's say, input pulse energy of 300 nanojoules, then we can measure a shear joining strength of 30 kilopascal. Okay. Then what happens if we double the input pulse energy and go to 600 nanojoules? Then the shear joining strength is 3 times lower, 10 kilopascal. Okay, so this is weird, but the main question is that sufficient? And sadly, the answer is no. Actually, in this case, the two materials are easily separable by hands, while typical values obtained for other material configurations or traditional bonding methods are on the order of 1 to 20 megapascal. So now we have to explain why. And when one wants to explain that, one has to recall that silicon is a medium where the propagation is highly nonlinear. For the reasons I mentioned previously about the nonlinear refractive index, which is 100 times higher than the one of fused silica, meaning that, for instance, let me give you an example. If you consider 1 microjoule input pulse energy, which is pretty typical, is the good order of magnitude for laser processing applications, then the peak power will be higher than the critical power for self-focusing for pulse durations below 20 picosecond. And this value of 20 picosecond is extremely high. And thus, as previously described, there will be this competition between Kerr effect and plasma formation together with defocusing, leading to the formation of a filament. Then the two consequences, I already talked about this. And again, there is a strong depletion of the energy deposition at the exit surface of silicon. So actually the interface between silicon and copper in our case. So the solutions we propose is, first, we use an interface with a metal, meaning that the absorption will be drastically increased, which is pretty good. And second, we propose a filament relocation method, to get an increased intensity at the interface between silicon and copper. But to do so, we need for nonlinear propagation imaging, and this is actually exactly what we did. We imaged the nonlinear propagation inside silicon by means of this setup, which is nothing else than an inverted microscope. And it allows us to evaluate experimentally the 3D fluence distribution inside silicon for different input pulse energies indicated here, and thus the nonlinear focal shift delta Z as shown here as a function of the input energy. In this data, 3 regimes can be distinguished. The first one for low pulse energy is, of course, the linear propagation regime as confirmed by point spread function analysis. If you want more details, you can check out those 2 references. This is a paper which will be soon published, and this is the corresponding software, which is open access. So I really encourage you to check this out. Then for intermediate pulse energy, up to 100 nanojoules, we can see that the focus is unambiguously shifted from the initial position in the linear configuration. However, the shape is conserved in this case. And the last regime for more than 300 nanojoules is that we are in the filamentation regime, sorry. And here you can clearly see it with the focusing and defocusing dynamics. So the conclusion of this is that increasing the input pulse energy will lead to an energy deposition far away from the interface, which is in good agreement with a semi-analytical model we have developed. You can check the corresponding papers I will give afterwards in the next few slides. So the question now is, can we push even more the limits? Well, to answer this, here I represent the shear joining strength between the silicon and copper for 2 input pulse energies, without in red and with in green precompensation of the nonlinear focal shift. And the striking feature from this figure here is that precompensating the nonlinear focal shift leads to a much better welding. Okay, so now the main question is, can we simultaneously keep this precompensation of the nonlinear focal shift delta Z strategy and increase the input pulse energy to get even more energy deposition at the focus? And the results are essentially shown here in the bottom. So the shear joining strength as a function of the input pulse energy, and you can see that around 1 microjoule input pulse energy, one can reach around 2.2 megapascal shear joining strength, which is quite suitable for applications. And the reason is that when you precompensate the nonlinear focal shift, you increase the maximum fluence at the interface, as well as the energy deposited at this interface. I mean, the energy reaching the interface, sorry. Then we observed, I mean, noteworthy, like here in purple is the nonlinear propagation threshold, and one can see that no welding is possible between silicon and copper for input pulse energies below 100 nanojoules, meaning that silicon to copper ultrafast laser welding is solely achievable in the filamentation regime. So you got, if you want to do this, you got to well, take into account the nonlinear focal shift and the filamentation. So here is the take-home message. So we demonstrated the first semiconductor and metal ultrafast laser welding because we characterized the filamentation induced by picosecond laser pulses inside silicon. Besides, we have demonstrated that megapascal shear joining strength were achievable, which are compatible with applications. If you want more details, you can scan this QR code here, which will lead you to our latest publication on the topic, which made the cover of Laser and Photonics Reviews a few weeks ago. So, to summarize, we can draw the following conclusions. In the femtosecond regime, in-volume laser direct writing in silicon is intrinsically limited by filamentation, which prevents the production of permanent modification inside the material. However, the produced underdense plasmas can be utilized for hacking microelectronic devices. And then in the nanosecond and picosecond regimes, the lower intensity leads to lower nonlinearities, and it is possible to modify and thus functionalize silicon with the inscription of optical elements inside the material for guiding, splitting, and dispersing light, for instance. And the best is yet to come, let's say. Also, the understanding of the nonlinear propagation inside silicon, especially the filamentation regime inside silicon, allows developing novel applications like semiconductor and metal welding. Before ending my talk, I would like to acknowledge some of my colleagues, especially my former supervisor in LP3 Marseille, David Grosjean, the group of Shooting Lay in Manhattan, Kansas, USA. Some of my colleagues from IM2NP concerning the microelectronic, studies. My colleague Stelios Tsortsakis from Forth in Greece, which did a lot of he did a fantastic job concerning the simulations for a better understanding of the filamentation regime. Of course, all my colleagues at IAP from the group from Stefan Nolte, so Markus Blotte, Qingfeng Li, Alessandro Alberucci, Chandrot Jisha, Helena Kammer, and Gabor Mateus. And finally, the postdoc of Stelios Tsortsakis, who work at Texas A&M in Doha, Qatar, Vladimir Fedorov. So I'd like to thank all of them. And also I would like to thank you for your attention. And ultimately, if you want more information, you can scan this QR code where you will see all the associated publications that I've shown today. And also you can alternatively contact me anytime at my address, so my professional address at the University of Vienna. Thank you.
Thank you, Dr. Maximi, for delivering a wonderful presentation. It's really amazing. So you have unearthed so many facts related to the lasers, and it's got this amazing performance. So
thank
really
you.
Wonderful. So behalf of the SRM IST Ramapuram campus and my own behalf, I would like to thank you for your spending your valuable time in our session. So now I call the audience to interact with the Dr. Maximi Chambano. You can ask your question. The audience, you are encouraged to ask the questions to Maximi. Any questions from the audience side? Dr. Maximi, sir, we have a few questions in the chat box. So,
let me check. So maybe I should share. Oh, okay. Yeah. Wow. Thank you all for your comments. So question about the dB, which is decreased to 4.5. What is the lowest losses that can be reached at least? The dislocation does not the crystal structure. So what is the origin of the dislocation? Dislocation does not modify the crystal structure. Okay. So concerning those dislocations, it's just that some atomic planes will slide up, I mean, one atomic plane will jump above the other. So actually there is no change in the crystallinity. However, there will be some reorganization. And concerning your first question, what is the lowest losses that are achievable? Well, to date, these 4.5 dB per millimeter are the lowest losses that can be achieved in silicon. Well, the lowest losses achieved in silicon with laser inscription technique. As I said before, you can check the publication of, I'm thinking about Professor Michel Lipson, working in the US in New York, who works on SOI, so silicon and insulator, and of course they achieve much lower losses. However, the SOI technique, as I said, it is not that convenient. It is really powerful, but we got to find some alternative, and this is the philosophy of my work, actually.
Okay. My question is, what is the purpose of making the wavelength lambda by 2 before the writing? In most of the slides I have watched that you have mentioned that the lambda by 2 after that. What is any special purpose for making that wavelength by 2?
So yeah, so sorry, this is so lambda by 2 means half wave plate. So this is a plate which allows to change the polarization direction. And when you combine it with a linear polarizer, it acts as a filter, like a tap, but for the laser energy. And then you can precisely adjust the laser energy.
Yeah, but what is the purpose of putting that half-wave plate in front of that?
Well, when you combine it together with the polarizer, so you rotate the polarization and then you filter some polarization. So it's not that you divide the wavelength. It's just that you rotate the polarization. It's called lambda over 2 half-wave plate, but there is no frequency conversion, like no nonlinear crystal. It's just some birefringent plate which allows to change the polarization orientation for adjusting the power.
Okay. Audience, do you have any question to Dr. Maxime, sir? Audience? Okay, thank you very much. Please stay with us, sir, for the validity function. Please stay with us.
Thank you.
Thank you.
Hi, Maxime. Hi, Maxime. Thank you so much for delivering a wonderful lecture. Please, within a minute, we will start a validatory function. Please join us.
Sure.
Please be in this meeting. And good evening, Professor Mohammed Joini.
No, it's okay. I asked 2 questions and I have got their answers. Maybe one. It's a nice talk, and I'm not physicist, but I really understand.
Yeah, we saw your message.
Yeah, thank you.
Please be in the meeting for 10 more minutes.